Hello, my dear students. So, this lecture will be the discussion about the Miller indices. So, in my previous lecture, I have explained about the uh, different types of solids and different parameters of crystal. So, here I'll be explaining about the Miller indices. So Miller indices are basically used by crystallographer, and it was introduced by the first. It was introduced by a British crystallographer. So this kind of indices is used to basically represent the planes and the direction of planes in the crystal. So if the crystal is one dimensional, then it will have one index, and if the crystal is two dimensional, then it will have two indices, and if the crystal is three dimensional, then that particular plane will have or can be represented by three indices. So here I have given a notation summary. So if we enclose these three indices, this Miller indices within the square brackets, then it represents the direction of the plane. And if we enclose these Miller indices within the angular brackets, then it represents the family of directions. And if we want to represent the plane, then we enclose the Miller indices within the parenthesis. And if we want to represent the family of planes, then we enclose this Miller indices within the curly brackets. So the steps involved for determining the Miller indices of a planes are given here. First, you have to find the intercepts of the plane on crystallographic axis. Then you have to take the reciprocal of those intercepts, and if the fraction has to be simplified, then just you have to multiply by the whole number. And if the simplification is not necessary, then whatever index we will get, we will enclose that within the parenthesis. That will be our required Miller indices of that particular plane. Now if any index will have a negative value, then instead of writing negative sign, we use a bar on top of that index. So let's go to the next slide. So in this next slide, I have given one example how to determine the Miller index of a particular plane. I have given here a plane. Okay, we can see here that this plane intercepts only on z-axis. So here the x-intercept, this plane is parallel to the xy plane. So the x-intercept and the y-intercept is infinity, and the z-intercept is 1. So if we take reciprocal of these intercepts, we will get 1 by infinity in the x direction, 1 by infinity in the y direction, and 1 by 1 in the z direction. So if we simplify it, if we, further, then we get 0 0 1. So since further simplification is not necessary, so we enclose this indices within the parenthesis. So this is our Miller indices 0 0 1. Now if you take a cube, then all the six faces will have similar kind of indices like 0 1 0, 2 0 will there, and there will be 1 or minus 1. So this represents same kind of planes. So this group of planes are represented by a family of planes, and the family of planes is represented by enclosing the Miller indices within the curly brackets. So normally to represent the all the faces of cube, we write 1 0 0 within the curly brackets. So let's go to the next slide. So in the next slide, I have given one plane. So here we can see that if I if we want to find the intercepts of this plane, we can see that the z intercept is right now -1. If I translate the origin, if I translate the origin along the z direction, then we can see that the z intercept is -1, y intercept is 1, and the x intercept is 1. So if you take reciprocal, you will get 1 by 1, 1 by 1, and 1 by minus 1. So since simplification is not necessary here as well, so the Miller indices of the given plane can be represented by 1, 1, 1 bar, and you should enclose within the parenthesis. So this is all for this lecture. Thank you. We shall meet in the next lecture. Okay. So this next lecture is about the diffraction of X-rays. So here, the reason why the X-ray is used to determine various parameters in the material science is because the the distances of I mean the interatomic distances in a solid are of the order of 1 angstrom. Okay, you can write it as 10 to the minus 8 centimeter as well. So if I want to find any parameters, or if I want to uh, like study different characteristics of the crystals, then the probe has to be the wavelength of the electromagnetic probe. The electromagnetic probe, the wavelength of the electromagnetic probe has to be of the order of that interatomic distance. So uh, so if I put so here I have given a the energy of photon, which is h bar omega. Okay, so if you expand it, then you can write it as hc by lambda. So hc divided by, so if I put this interatomic distance equivalent to the wavelength of that electromagnetic probe, then we will get an energy of that particular photon, which is which we have got here, 12.3 into 10 to the 3 ev. Okay, so 10 to the 3 ev energy is corresponds to the x-rays. Okay, characteristic x-ray energies. So now, how this diffraction occurs, how this diffraction occurs, is and how this X-ray is diffracted by these crystals. So now, since we know that the crystal is an or lattice is an periodic has a periodic array of lattice points, or you can say the group of atoms, ions, or single atoms as well. Okay, so in a crystal or in a lattice, they are arranged in a periodic manner, and provided that the periodicity is of the long range order. Okay, so if it is short range order, then it will be polycrystalline. There will be various kind of crystal. So therefore, since it is long range order, so it will be a pure crystal. Okay, so when X-rays interact with such kind of periodic arrangement of atoms or ions or group of atoms, then it interacts elastically with the electrons of the atoms in the crystal. So for the clearance of understanding, since there are lots of electrons within the atoms of the crystal, so we will say that we will talk about the electron clouds rather than speaking about individual electrons. It will be electron clouds actually. Okay, so we will so when the x-ray when the incident x-ray interacts with the electron clouds, then the electron cloud starts oscillating with the same frequency as that of the incoming x-ray. Okay, this why? Because of since it is an elastic collision, that's why there will be no loss of energies. Okay, I mean the x-ray, the incident x-ray will not impart its own energy, or it cannot be absorbed. If the x-ray, if the energy of the x-ray is absorbed, then what will happen? Then the energy will be extracted by those electron clouds, isn't it? So here, since it is the elastic collision, so the it will not absorb, rather it will collide elastically, and it will make the electron clouds start oscillating. And this oscillation is such that the frequency of this oscillation is similar to that of the frequency of the incoming X-ray. Therefore, the oscillating electron clouds, uh, the whatever electromagnetic radiation is emitted by the electron clouds, those will have the frequency equal to that of the incoming X-ray, and therefore uh, therefore this you can see here, this oscillating electron then emits the electromagnetic radiation whose frequency is same as that of the incident X-ray beam, and this kind of scattering is called elastic scattering. Okay, there is no any loss of energy. uh, the incident beam has not lost its own energy. Okay, the whatever beam has been emitted, it is a secondary emission. I have shown here as a I have tried, I have drawn here a schematic, I mean exaggerated schematic diagram. Okay, when an X-ray incoming X-rays interact elastically with the electron clouds, the electron cloud starts oscillating in their mean position. So this oscillating electron clouds now emits uh, electromagnetic radiation, which we call a secondary emission. Okay, now this emitted electromagnetic radiation, uh, depending on the orientation of the planes, they will either interact constructively or either they will interact destructively. So if they interfere constructively, then we will observe the constructive interference in the detector. So amorphous materials like glass or mica, they do not have a periodic array of long range order, so they do not produce a diffraction pattern. So next we come to the Bragg's law. So till to this date, this law has not been changed, and this law is still used in material science. If you go for the higher studies, then you will see that this law is still used, and the XRD is the most of most I mean uh, oldest technique I think in the material science, which is still being in use uh, to study different characteristics of the material. So in 1912, 12 and W.H. Bragg and W.L. Bragg put forward a model. They forwarded a model, and that model considered that a crystal can be divided into various sets of parallel planes. Okay, and those planes can be assumed to be smooth like a mirror. Okay, now, and they assume that the diffraction lines formed can then be accounted as if X-rays are reflected by such a set of parallel planes. Okay, now they in their model they have assumed like these planes act like a smooth mirror. Okay, uh, and since it is X-ray diffraction, but in their model they have assumed in such a way that this diffraction pattern is because of the constructive interference of this reflected X-rays. So based on this consideration, Braggs derived a simple mathematical relationship which is still in use until to this date. Okay, which serves as a condition for the Bragg reflection to occur. So this condition is known as the Bragg's law. So derivation of Bragg's law here I have given, which is usually asked in your examination, either the numerical or either the derivation or both. So here in this derivation, it is considered a set of parallel planes, as I have said before. Okay, the set of parallel planes, and since they are parallel, so all these planes will have the same Miller indices h, k, l. Okay, it will not have h1, k1, l1. It will have same Miller indices since they are parallel. So between these two planes, the interplanar spacing we call it is denoted by d, small d, and having Miller indices HKL. So let a parallel beam of X-ray has a wavelength lambda, okay, incident by some angle, making some angle with the plane of the crystal. Let's say the angle is theta. Okay. Now let us assume two rays. We cannot count rays, okay, but here for the simplicity, for making the calculation simpler, we have assumed here two rays. One of the ray strikes the first plane, and the second ray strikes the second plane. So the diffraction pattern observed is the consequence of constructive interference of this reflected rays. So these reflected rays, when interfere constructively, then only we can see the interference pattern. Now this interference pattern will depend on this angle theta. If there are some there will be some allowed angle for which condition we can see the constructive interference. Okay, that's why it is called Bragg's condition. Sorry. So now here AB and AD is the perpendicular drawn from A on the incident and reflected portion of the ray respectively. Here in the diagram you can see from the point A I have drawn a perpendicular AB on the second incident ray and AD perpendicular on the second reflected ray. So since they both the ray follows the law of reflection, so if you use a geometry you will see that this angle whatever this angle is, the same angle will be this one. So I have assumed it as an angle theta. uh, Whatever angle you have seen here, the same angle we will get here. Okay. uh, so now this the dashed line is same as D. So I can write BC as d sine theta and CD as d sine theta. So the total path difference is, see, the extra path traveled by this second ray is BC plus CD. BC plus CD. So BC can be represented by d sine theta, CD can be represented by d sine theta. So the total path difference will be 2d sine theta. Now this reflected rays will interfere constructively only when the it will be an integral multiple of lambda, integral multiple of the wavelength. Okay, so this if this path difference is an integral multiple of this wavelength, then only we can see the constructive interference on the detector. So this condition, finally we come to this condition, 2d sine theta is equals to n lambda. So this is called the Bragg's law. So for n equals to 0, we get zeroth order of reflection which occurs for theta equals to 0, that is in the direction of incident beam. Okay, that means the direction from which the incident beam was coming, the reflected ray is going back towards the incident beam. So then we cannot see in the detector, right? So that's why the theta equals to 0 is not possible condition. Therefore for n equals to 1 and n equals to 2, n equals to 3 represents first, second, and third order diffraction lines respectively. Okay, and the detector, remember that whenever you will see in numerical, there they will give the value of 2 theta because the detector which is used to measure this angle theta, the detector is measures the angle 2 theta actually. It measures this 2 angle 2 theta. That's why you have to simplify it, the 2 theta into theta, while solving the numericals. You will see in the example. So the intensity of the diffraction line decreases with increase in the value of n and theta. Okay, and for simple cubic crystal, so since in your syllabus on the questions will come based on the simple cubic only, so don't bother about the other type of crystals. So for simple cubic crystals, the relation between interplanar spacing d and lattice constant a is given by uh, if d is the interplanar spacing between two planes and the dead planes are having mirror indices hkl, okay, then the relation between this d and the lattice constant a is given by this relation. So we will use this relation in the example. Here I have given one example. A BCC molybdenum sample was studied with the help of an X-ray diffraction using X-ray of wavelength 1.543 angstrom. Diffraction from 200 planes was obtained at 2 theta. See here, 2 theta. The detector will always measure 2 theta. So it is given as 60 degree. Assuming the diffraction to be of first order, that means n is equals to 1. Okay, determine the value of lattice parameter. Lattice parameter means we have to determine A. So wavelength is given 1.543 into 10 to the power minus 10 meter. HKL is given as 200. N equals to 1. 2 theta is equals to 60 degree. So theta will be equal to, see here, 30 degree. So lattice constant we have to determine. So we use the simple formula which I have given in the previous slide. D200 is equals to A by this. So we will get A by 2. Further from Bragg's equation, we have 2d sine theta equals to lambda since n equal first order reflection. So therefore n equals to 1. So A sine theta is lambda, A equals to lambda by sine theta. So we put the value of lambda and theta, then if you calculate it, you will get A equals to 3.086 angstrom. So here I have given some exercises for you to solve it. So I hope please solve and submit it in my Google Classroom. So here I have given a link of a YouTube video in which the experimental video of X-ray diffraction is given. You can go here and check it out to for your clear understanding. And if you still have any doubt, then you can ask me. Don't hesitate to ask me. Uh, so finally, thank you.